Hi, all. Welcome back to the paging series of operating system. And in this lecture, we are going to learn about multi-level paging. And already we have seen some features of multi-level paging. What does this? Why do we need multi-level paging in memory management? And in this video, we are going to learn about some questions and also how what is the performance when we introduce this multi-level paging in the memory management. Okay, so let's start with one question. Let's say that we have a system, and this system is having a two level paging system. Okay, so whenever we say two level paging system, it stands for the multi level, and the page table is divided into 8k pages. So page table divided into 8k pages, each page having 16k entries. Okay, so each page is having 16k entries, and the memory is byte addressable. Okay, memory is byte addressable. Okay, so now if we say that we have a PAS, physical address space, as 128 megabyte, and it is divided into 4k frames, that is number of frames equal to 4k. So we can calculate from here that therefore the frame size, or that is equal to the page size, is equal to 128 into 2 to the power 20 upon 2 raised to the power 2 into 2 raised to the power 10, and that is equal to 2 raised to the power 8, and this is 2 raised to the power 7, 2 raised to the power 8, 2 raised to the power 15. Okay, so the page or frame size is 2 raised to the power 15 byte, that is equal to 32 KB. So we have got the page size. Now we have said that the page table entry size in both the levels. So there are two levels. So the PTE in both the levels is equal to 32 bits. Now 32 bits is how many bytes? Is 4 byte. So we have been given the PTE. Now assuming that for the page table which is divided into 8k pages, so what does happens that this is our page table, and this page table is divided into some 8k pages. So definitely for this 8k pages we have made this page table, the second level page table. So here we have altogether 8k pages, that is 2 raised to the power 13. So if there is the logical address P and D, so here P can be divided into P1 and P2. So this P1 corresponds to obviously 13 bits. Now this 13 bits are used to represent these pages of the page table. And what does this P2 correspond to? So we have said that each page is having 16k entry. So this page is having 16k entries. So here the page offset is 16k, that is 2 raised to the power. That is the size of each page of the page table is 16k W, or yes, 16 kW. So it is the offset, that is P2 here, is 2 raised to the power 4 into 2 raised to the power 10, that is 14 bits. Okay, so we have got the P2 as 14 bits, right? Now if someone asks about the length of LA, so LA is equal to P1 plus P2 plus D. So it's 13 plus 14 plus D is we already have calculated, that is the page size, right? So that is the page offset. So this is equal to 32 KB. So it is 32K. So 2 raised to the power 15. So this is 15. So altogether it is 27 plus 15. that is equal to 1242 bits. So we have calculated the LA as 42 bits. Just a second, let me see. This is 15, right? 2 raised to the power. hmm This is 13, 14, and D is equal to the page size. So page size is 12, and this is 8. This is 2 raised to the power 7. So 2 raised to the power 15. So page size is 2 raised to the power 15. So it is 32K. So, okay, okay. Just a second. Why it is not matching with the answer? Mm, so it is 27 and 4 KB and it's 128 MB. So frame size is okay. I think here is this problem. So it is 128 MB. So 2 raised to the power 20, right? And okay, why it is 4 KB frame size or page size? Okay, it's not 4 KB. Total number of frames is 4 KB, right? So I did some mistake here. Let me correct it. So it's actually the frame size or page size. Okay, let me recorrect it. So it won't affect that much, but here instead of the total number of frames, we are taking the page size and frame size. Okay, so here the frame size is given as 4 KB. Okay, so if the frame size is 4 KB, so here from here we can calculate the D as equal to, because a frame size is equal to the page size, and page from the page size we can calculate this page offset. Okay, so that is equal to 2 raised to the power 12 byte, and so we calculate D as 12 bit are used to represent the page offset. Okay, now if we add it here, so it's 12, so it will change. So it will be altogether 39 bits. Okay, since the answer was not matching, so I looked back to the question and now I got. Okay, now LA we have calculated. PA, if someone asks, so PA is nothing but frame size. We can calculate it from the PAS. So PAS is 128 MB. So it will be 2 raised to the power 7 into 2 raised to the power 20, right? And this will be equal to 27 bits is the PA. So PA we can calculate from the PAS only. Now first level pace table size, that is important, which is related to our multi-level paging. So in first level page size, we can calculate the number of entries into entry size. Now, entry size is fixed for both, that is equal to 32 bits and this is equal to 4 bytes. But number of entries into this first level page size is equal to the number of pages in which we have divided this page table into. So we have divided this page table into 8K pages, right? So it is 2 raised to the power 13. So if we calculate the total number of entries, it is 2 raised to the power 13 and it is 2 raised to the power 2. So it is altogether 32 KB. Okay, because 2 raised to the power 13 is the total number of entries, total number of pages in which the page table has been divided into, right? Now, if we say that what is the second level page table size, So second level page table size is equal to also number of entries, number of entries into the entry size, right? Now entry size is gonna fix, that is 4 byte. Now number of entries in the second level page table size is equal to the page offset. So if we have divided it into 2 to the power 13 pages, so each page, so here if let me represent it here. So this is our page table, and this page table is have been divided into 8k pages. Okay, so here we are maintaining another page table for this 8k pages. So it is gonna have 8 uh, 0 1 altogether, 2 to the power 13 minus 1 entries. Now this will contain the base address, base address of this particular page of the page table. So if we get it here from P1, we get to this point. Now here we have this page offset. That page offset is the size of this page. Okay, so each page is having 16k entries. 16k entries. So this is the size of the page of the page table. So 16k determines the entries of uh, s- uh, the entries of this particular page. Okay, so if we talk about the second level page table, so this is the first level page table, and second level page table is nothing but this page will be bought, and it will be having this altogether 16k entries. So 0 1 and so on up to 2 raised to the power of 14 minus 1 entries, right? So this will be having 16k entries, and this will contain our frame number. Okay, so here it will be second level page table size is equal to number of entries, that is equal to 2 raised to the power 14 into 2 raised to the power 2, that is 4 byte. So it is altogether 64 kilobyte. So second level page table is 64 kilobyte. So this is the way we do the multi-level paging. The important thing that here I wanted to discuss is the performance of two-level paging. When we introduce this two-level paging, it's two-time level, two-level paging. So what is the total access time? So let's say with we are using it without TLB. So as we have seen for paging also, without TLB, if we are using, so first time we are accessing the first level as is as M. The second level we are accessing, it takes M. So M is the main memory access time, and the third time we are accessing it from for the particular fetching the particular page from the frame. So it's altogether 3M. So if it is a two level paging, so it takes N plus 1 into M access time without TLB, where N is the level of paging. Okay, but now if we say that we are using with TLB, I mean, if TLB is added to improve the performance. So in case of paging, we saw that the TLB consists of the frequently referred pages and their corresponding page number, right? So here also, if we see that the TLB access time is, let's say, C, and TLB main memory access time is M. So what is the EMAT if we need to calculate? So let's see what it will be. So if we have this CPU is generating, the processor is generating this address that consists of P and D, where P is the number of pages in the virtual memory and D is the page offset. So here it gets divided into P1 and P2. Okay, when paging is applied, so it is two level paging. Now from P1 contains the number of pages of the page table. So in normal case, what will happen, that this will go to this page table, which is the first level paging, or you can say outer paging. Okay, so it contains the number of pages of the page table, and from here we can find the base address of the page table that we want to access. Okay, we get the base address of the page table that we want to access. Now P2 will contain the total number of entries of the page table. Okay, so P2 will contain the page offset of this particular page that we have fetched, and from here we are going to get the frame number corresponding to the page. So here we are getting the frame number and page offset, and from here we can access the main memory to fetch the particular page, right? So in normal case it requires m plus m 3m time, but let's say we have introduced a TLB here. So now instead of looking into here, the processor will be looking into the TLB, translation look-aside buffer, which contains some frequently referred pages along with uh, the frame number in which the page is present. So if it is a hit, let's say if it is a hit, so here we are just going to corresponding to the page number P, we are getting the frame number. And just let me change my sketch pen color. So if we are just if it is a hit, right, if let's say it is a hit, just a second, let's say if it is a hit, so what will happen is it will directly go into this main memory and fetch this particular page, right? So accessing this takes c time and accessing this takes m time. So when it is a hit, let's say if x is the hit, so it takes c plus m time only, because here we don't require to do go through this whole step. Here this is the page number and this is the corresponding frame number of the most referred page, because this is a TLB, right? Here we can get a page corresponding to the frame number, I mean the frame number corresponding to the most referred page. Okay, so from here only we can just go to the main memory to fetch that particular page. So it is a x into c plus m. Now let's say if it is a TLB miss, okay, that is if we are not finding it here. So let's say if it is a miss, so now we have to go to this entire process of getting back the page. So it will 1 minus x accessing the TLB, plus we have to go through all the levels, that is n plus 1 into m. Okay, so this is the effective memory access time in case of second level multi-level paging, right? So this is all about the paging. Some important point to note here is in multi-level paging, when paging is applied on page table, then the page table last page table we get is called the first level page table, is called first level page table. Okay, this is first point. The second point is that in multi-level paging, when paging applied on paging applied on page table, then first level page table entry contains the base address of second level page table. Second level page table entry contains base address of third level page table, okay, and so on, okay. And the final level page table contains the entry, page table entry, which contains the frame number of actual page. Okay, this is one thing. Then the third thing is when paging applied on page table, when paging applied on page table, whatever may be the levels of paging, whatever may be the levels of paging, all the page table are stored in the main memory. Okay. Then fourth point is in multi-level paging, when paging applied on page table, whatever may be the levels of paging, whatever may be the levels of paging, all page table entry contains the number. Okay. If page table size is not mentioned in any problem, so if page size is not mentioned in any problem, then page size will be same in all places or in all levels. Then page size is same in all places or all levels. Okay. In typically window follow page size of 4 kilobyte. Okay. So if we diagrammatically draw this, so this is, let's say, the first level page table. This is the second level page table. This is the third level page table. Okay. And this is, let's say, the main memory, and this is the virtual memory. So this is PAS and this is LAS. Now, first of all, we are applying paging on this. So let's say we are applying here paging this way on this particular page table. So now here, this will definitely be containing the frame number. Okay, because this is the last level of paging. So this is containing the frame number. Now, for each of this, we have the corresponding entry in this level. So when we apply paging for each of the page, we are just having this kind of entry. And here this contains the base address of this part. Okay, so if this contains the base address of this like this. Again, if we are applying paging onto this, then for each of them, we are having this entry here like this, and it contains the base address of this. So if we say that this is the first level of page table, this is the second level of page table, and this is the third level of page table. So in this way, the number of bit of X is equal to the number of bit of in y is equal to the number of bit in f. Okay, so the LA will be something like this. So if this is the logical address, so the logical address will be divided into P1, P2, P3, and then D, where P1 stands for first level of indexing, P2 stands for second level of indexing, and P3 stands for third level of indexing. And number of bits in X equal to number of bits in Y equal to number of bits in F. Okay, so these are equal. So this is all about paging. There are certain questions related to that. We can see them more. One of the important thing here is like we already have discussed all three types of paging. Now the question comes like let's say if there is a system. Okay, let's consider this question as a part of the series only. So let's say we have a system with a logical address given as 46 bits, and then we have the physical address which is given as 32 bits, and memory is definitely byte addressable. So memory is byte addressable. Now, if we say that PTE, that is the page table entry, it is equal to 32 bits. Let's say 32 bits is nothing but 4 bytes, right? And OS has three level of paging, okay, for mapping the logical address to physical address. And the first level of page table size, first level PT size is exactly same as page size. Page size, then what is the page size? So we already know that page size comes up from here or here. So we need to know that what in what ratio we have divided in the page size. So if we have this logical address as 46 bits, so definitely what will be the LAS? 2 raised to the power 46 byte, right? And if we are here, we are given the PTE as a 4 byte. Okay, so PTE will definitely contain the frame number. Okay, so if it is saying that it is 32 bits, PTE is 32 bits, so total number of frame could be taken as, so from here we can write that total number of frames, total number of bits required to represent a frame is 32 bits, right? So if we are saying that total number of bits required to represent a frame is equal to 32 bits, then definitely what will happen that number of frames is equal to 2 raised to the power 32. Okay, so number of frames is 2 raised to the power 32. So frame size, if we calculate, it is equal to 2 raised to the power 32 byte upon 2 raised to the power 32. So it is 1 byte. So frame size is 1 byte only from this, right? But here, and page size obviously will be equal to, page size is equal to 1 byte only, because the page size is equal to the total frame size, right? Now, let's say here we are saying that we don't know in what ratio things have been divided, right? We all just know, we just have the LA, PA, and PTE. PTE is 4 byte. Okay, so let's say that we have this grouping. So we have this first level, we have this second level, and we have this third level, which contains the frame number. Okay, so frame number is here for the PA. Now, here we don't know how many pages it has been divided into, and we don't know what is the page size. So, if the page size is not given, then we can assume that the page size in each of them is the same. That is, we are assuming the page size to be the same throughout. That is equal to the page offset, that is D. Okay, so page size is assumed, let's say P throughout. So we have been dividing this into P size frame, P size pages. So number of pages, number of entries in which it is getting divided. Let's say this page table size. Okay, we don't know the page table size as well. So okay, so this is the third level, and what is the total number of LA is equal to 46 bit, right? So the total number of pages, and okay, we have calculated the page size, that is equal to 1 byte, right? So the total number of pages in this would be 2 raised to the power 46. And let's say we have divided into P size pages, so it is P. So in this, if we say that the total number of entries will be 2 raised to the power 46 upon P. Now again it is divided into P size pages. So in this, if we calculate the total number of entries, it will be 2 raised to the power 46 upon P, divide by P, so it is P square. Okay, so this is the total number of entries into this is the total number of entry into this. Okay, right, and this, the total number of entry here is 2 raised to the power 46. Okay, so for all these three we have calculated the total number of entries. Now it is saying that the first level page size is, sorry, what is the question? Let me go back to the question. So it is saying the first level page size is exactly same as the page size. So first level page size is this, 2 raised to the power 46 upon P square. It is same as the page size. So page size is how much? Page size is, okay, and we are not multiplying it by page table entry, that is 2 raised to the power 2. So this is 2 raised to the power 2 into 2 raised to the power 2. So this is 2 raised to the power 4. Okay, and yep, uh, page size is P, so number of pages. hmm I think I did something wrong here. Let me recall. Okay, okay, we are not multiplying it by 4, right? hmm Okay, let's reconsider this question once more. I think I did some mistake somewhere. Just let me recall this question. So we have three levels of pages, right? So this is the first level, this is the second level, and this is the third level, which contains the frame number, right? And here we are given that the PA is equal to 46 bit. Okay, so if the PA is 46 bit and PTE we have been given as 4 byte, and memory is byte addressable. So PAS is something called 2 raised to the power 46 byte. Let's say the page size is P. Okay, so number of pages in the third level is 2 raised to the power 46 upon P, right? 2 raised to the power 46 upon P. So if we calculate the page table size of this, it is 2 raised to the power 46 upon P into 2 raised to the power 2, that is 2 raised to the power 48 upon P. So this is the page table size of this. Now this has been divided into P equal size pages. So number of entries into this will be 2 raised to the power 48 upon P squared, and total size will be into 2 square, that is 2 raised to the power 50 upon P square, right? Now This is the size of this. Now this has been divided into p equal size pages. So for the third level, it will be 2 raised to the power 50 upon pq into 2 raised to the power 2. This is the size. Now this size is equal to the page size, so it will be 2 raised to the power 52 equal to p to the power 4. So p equal to fourth root of 2 raised to the power 52, right? Or we can say it as if xp4 equal to 2 raised to the power 52. Okay, we are considering this way, so we can write it as we can calculate like 2 raised to the power 13 into 4 equal to p raised to the power 4. So p equal to 2 raised to the power 13 and it is equal to 8 kb, right? So this way we can calculate, right? So please ignore this part. I think I did some mistake here. So, yeah, this is all about the multi-level paging, and next we will see segmentation and segmented paging. So, I'm just closing the lecture here. If you do have any questions or doubt or comments, please do post in the comment section. Thank you very much.